Welcome to qnawire.
This is a question about the decay of the uranium-238 nucleus by the emission of alpha particles. So this question gives us a lot of data. It gave us the behavior of the nuclear potential as a function of the radius. It gave us these two equations that we are going to use, but not at the beginning of this question, and it also gives us some data about the uranium-238 and the alpha particle. We begin this question by solving the first item. In that item, we have to assume that the alpha particle is a point particle, that the nucleus has 8 femtometers of radius, and then we have to evaluate what is the peak of the potential barrier. For that, we have to use this expression that the problem gave us of the potential as a function of the radius. As we want to evaluate what is the potential at this point, at the peak, we have to calculate what is the value of u when the radius is equal to the radius of the nucleus, since this maximum happens precisely at the surface of the nucleus. It goes as follows. U, which is the value of the potential at the peak, is equals to the charge of the alpha particle, which is 2 times the charge of the electron, times the charge of the uranium nucleus, which isn't 92 but 90, because out of this 92, 2 of these charges are due to the alpha particle. So we are left with 90 times the charge of the electron. Then we divide it by 4 times pi times epsilon 0 times the radius of the nucleus. Now we plug in the values that we have to get the following. U at the peak is equals to 2 times 90 times E squared, remembering that E is equals to 1.6 times 10 to minus 90 according to this additional data that we need. So here we have 1.6 times 10 to minus 19 squared. Then we divide it by 4 times pi times epsilon 0, but 1 divided by 4 times pi times epsilon 0 is equal to 8.988 times 10 to the 9th. So instead, we multiply it by this value, which is equal to 1 divided by 4 times pi times epsilon 0. So here we have times 8.988 times 10 to the 9. And finally, we have to divide by the radius of the nucleus, which is given by 8 femtometers. Each femtometers is equals to 10 to minus 15 meters. Now, solving this calculation will give us a value of energy in joules, but since we are dealing with nuclear properties, we would rather evaluate this energy in electron volts. In order to convert from joules to electron volts, all you have to do is divide the energy by the charge of a single electron. So we add an extra factor of 1.6 times 10 to minus 90 to convert the result to electron volts. But this conversion factor will actually help with the calculation, because we can simplify it. Now, by solving this calculation, we get a value for the peak of the potential that is 32 times 10 to the 6th electron volts, and this is only approximately. And then we can write it as 32 mega electron volts, since 10 to the 6 is the same as a mega. Therefore, this is the answer to the first item of this question. Before going to the second item, let me organize my board. In the second item, we are told that when free, the energy of the alpha particle is approximately 4 mega electron volts. Given this information, we have to give an estimate for the width of that potential barrier. We will proceed as follows. Take a look here at the plot of the potential barrier. What is the width? The width is this quantity, this distance from this point to this point. This is the radius of the nucleus, and this is the radius of the exit, let me call it like that. Then the width, which is this quantity, is given by the radius at the exit minus the radius of the nucleus. So, just like this. Now, how can we evaluate this quantity? We begin by evaluating what is the radius at the exit. For that, we use this expression. So, the potential at the exit is equals to Q times Q divided by 4 times pi times epsilon 0 times the radius at the exit. Now we perform a small algebraic trick, which is multiplying and dividing by the radius of the nucleus. By doing that, you get the following. Q times Q divided by 4 times pi times epsilon 0 times the radius of the nucleus. This is just the peak of the potential barrier, which we know that is approximately 32 mega electron volts. Then this becomes the following. The potential at the exit, UV, is equals to the potential at the peak, U peak, times the radius of the nucleus divided by the radius at the exit. Then, using this expression, we can solve for the radius at the exit to get the following. The radius at the exit is equals to U peak divided by U exit times the radius of the nucleus. Now, all we have to do is plug in the values that we have and get the value for the radius at the exit. Plugging in the values we have, we get the following. UP is 32.36. Notice that for this calculation, I'm using the full value for the potential at the peak and not this approximated value. Now we divide this value by the potential at the exit, which is 4 mega electron volts, and then we multiply by the radius of the nucleus, which is 8 femtometers. By solving this calculation, we get a radius at the exit that is 64.72 femtometers. Now, all we have to do is evaluate the width of the barrier. So, delta R is equals to 64.72 minus the radius at the nucleus, which is 8, and this results in approximately 57 femtometers. And this is the answer to the second item of this question. Before proceeding to the next item, let me organize my board again. In the third item of this question, we have to begin by modeling this potential as a square well. We do it as follows. So this is from 0 up to R, but there is a spherical symmetry in the nucleus. Therefore, we actually have one potential like this to the right and another potential like this to the left. So, modeling this as a square well goes as follows. We have one potential modeling this potential to the right, and another potential just like that one modeling that same potential to the left. This region in between the barriers is inside the nucleus, and this region is outside the nucleus as well as this one. The question asks us to use a width that is 1/3 of the actual width of the full potential. Then this is just delta R divided by 3, just like this. The in region actually measures 2 times the radius, so the inside region is actually the diameter of the nucleus. Now, given that, we have to calculate the speed of the alpha particle, how often it hits the barrier inside, and then give an approximation to the lifetime of the uranium. We begin by calculating the speed. We know that the free alpha particle has an energy of 4 mega electron volts, and the alpha particle is free in this region, and in this region. It isn't free when it is inside of one of those barriers. So inside the nucleus, the alpha particle is free. Then all of its energy is just kinetic energy. So we can say the following. The kinetic energy of the alpha particle is equals to 1 divided by 2 times the mass of the alpha particle times its speed squared. Notice how it is just the usual expression for the kinetic energy. Okay, now we solve this expression for the speed. This gives us the following. The speed will be given by the square root of 2 times the kinetic energy divided by the mass. Now we plug in the values that we have for those quantities. We have 2 times the kinetic energy, which is 4 mega electron volts, but we want a velocity in meters per second. Therefore, we better convert these 4 mega electron volts into joules. In order to do that, we begin by eliminating the mega, so we include the 10 to the 6th here. Now we have 4 times 10 to the 6th electron volts. In order to convert from electron volts to joules, all we have to do is multiply this quantity by the charge of a single electron, which is 1.6 times 10 to minus 19. And that's it. Now we divide it by the mass of a single alpha particle, and the problem told us that the mass of a single alpha particle is 4 times the mass of a proton. Then we have 4 times the mass of a single proton, which is 1.67 times 10 to minus 27. By solving this calculation, we get a speed that is approximately 1.38 times 10 to the 7th, which we can further approximate to 1.4 times 10 to the 7 meters per second. And this is the first answer. Now let me organize my board before proceeding to the next ones. Okay, now let's evaluate the frequency with which the alpha particle hits these two barriers. We know that the speed is given by the ratio in between some distance and the time it takes for something to travel that distance. In this case, we are talking about the free alpha particle inside the nucleus. So the speed is given by this value that we had just evaluated. The displacement, or the distance it's traveling, is given by 2 times the radius of the nucleus, and delta t will be the time it takes for the alpha particle to travel from one barrier to another. What we want to evaluate is the frequency, that is the inverse of this time. Then what we want to evaluate is 1 over delta t and not delta t itself. We can evaluate 1 over delta t as follows. 1 over delta t is equal to the speed divided by the displacement. And then we just have to plug in the values that we already have. The speed v is equals to 1.38 times 10 to the 7th. We approximate only at the end of each of these calculations. And then we divide by the diameter of the nucleus, which is 2 times the radius, which is 8 femtometers, so 10 to minus 15 here. By performing this calculation, we get the following. The frequency, which is 1 over delta t, is given by 8.625 times 10 to 20, which we can approximate to 8.6 times 10 to 20 collisions per second. And this is the second answer to this item. Now, before proceeding to the final answer, let me organize my board yet again. Now for the last answer, we begin by calculating what is the tunneling probability, that is, what is the value of t given the data that we have. For that, we will need to evaluate this auxiliary quantity g. So let's begin by evaluating g. G is given by the square root of 2 times the mass of the alpha particle, which is 4 times the mass of the proton, and the mass of the proton is 1.67 times 10 to minus 27 kilograms. Then we multiply it by U0 minus E. U0 is the height of that square barrier, so 32.36 mega electron volts. And E is the energy of the alpha particle, which is 4 mega electron volts. Now we convert from mega electron volts into electron volts. We accomplish that by multiplying by 10 to the 6th. And finally, we convert from electron volts into joules, which we can accomplish by multiplying by the electron charge, which is 1.6 times 10 to minus 19. Then we take the square root and divide by h bar. The value of h bar is 1.055 times 10 to minus 34. By solving this calculation, we get g as being approximately 2.33 times 10 to the 15 meters to minus 1. Now that we have the value of g, we are ready to evaluate the tunneling probability t. It goes as follows. The tunneling probability t is given by the exponential of minus 2 times the value of g, which is 2.33 times 10 to the 15 times the width of that barrier, which is delta r, or more precisely 56.72 femtometers divided by 3. Now we have meters to minus 1 here in g, so we have to convert from femtometers here into meters. We accomplish that by multiplying by 10 to minus 15. Solving that calculation results in t being approximately 5.451 times 10 to minus 39, and this is a dimensionless quantity. Also, as you can see, the tunneling probability is very small. Okay, now that we have the tunneling probability, we can multiply it by the frequency, and the product in between the tunneling probability and the frequency, f times t, is the frequency of the decay. That is, out of 8.6 times 10 to the 20 collisions that happens each second, only f times t are actually decays. So let's solve this calculation. F times t is 8.625 times 10 to the 20 times 5.451 times 10 to minus 39. And this results in approximately 4.702 times 10 to minus 18 decays per second. So as you can see, the decay rate is very, very small, meaning that we expect the uranium to have a large lifetime, which we can estimate by taking the inverse of F times T. That is, the lifetime can be approximated by 1 divided by F times T, which results in 1 divided by 4.702 times 10 to minus 18, and this is approximately 2.127 times 10 to the 17 seconds. As this is a very large value, we can have a better visualization if we convert this from seconds into years. For that, all we have to do is the following. We have to divide this by the number of seconds in each year. Each year has 365 days, each day 24 hours, each hour 16 minutes, and each minute 16 seconds. And this results in approximately 7 times 10 to the 9 years. This is the lifetime of the uranium, and this is the final answer to this question, 7 times 10 to the 9 years.